Hi everyone, here we are on chapter 19. So chapter 19 we are going to split into two parts. So we're going to have a test on sections 1 and 2, and then we're going to have a separate test on sections 3 and 4. Okay, so this lecture is just on section 1, and this is going over what we call reaction rates. Okay, so a reaction rate is basically how fast it takes for the reaction to take place. Okay, so remember, in a chemical reaction, the reactants are being used up. Okay, the reactants are being used up. That's why it says right here, when the reactants disappear, and then eventually over time, right, products are going to be made. All right, and so obviously the reaction is the fastest at the beginning of the reaction. And the reason why it's fastest at the beginning is because that is when the reactants are in the highest concentration. And then eventually, over time, it's going to slow down because the reactants are being used up. Now, in order for a reaction to take place, it is all based on what is called the collision theory. So, in order for a reaction to take place, the particles and the molecules and stuff are colliding and hitting each other, okay? But they have to collide and hit each other in the right orientation. So, they have to collide in the right orientation, and they also have to have enough what we call activation energy. Okay, so activation energy is the minimum amount of energy required for the reaction to take place. Okay, and we're going to talk more about that. So this picture is showing you how the molecules have to hit and collide in the right orientation. So if we take a look here, okay, so if we have these two molecules react, they collide in that orientation, notice we'll get the product of diatomic bromine and then two NO molecules that we're looking for. The molecules can collide and hit in this orientation. Notice that will still give us the diatomic bromine and then your two NO molecules. But if they get flipped around, notice here that there's no way that the diatomic bromine can form. So that's why that one is no reaction. So this picture is just demonstrating how the molecules have to collide in the right orientation in order for products to be produced. And then the other requirement that we talked about the activation energy or the activation barrier. So that is what the EA represents, and I'll circle it right here. Okay, so big E for energy, and then the little a for activation. Okay, so that's activation energy. Notice some things I want you to recognize on the graph. You have to be able to label a graph and understand what this graph is telling you. On the left side here, where the reaction is beginning, that will be the reactant side, okay? And then over here on the right side, these are going to be your products, okay? So reactants are always on the left, products are on the right. So at the beginning of the reaction here, the molecules are hitting and colliding with each other, and then they have to collide and hit each other not only in the right orientation, but have enough energy to get over the hill, okay? Once they're over the hill, then products can be made. Okay, so the analogy that I like to use is like running up a hill. Okay, like running up a hill. So imagine running up this hill here, you have to have enough energy. Okay, you have to have enough energy to get up and over the hill, and then once you're over the hill, then it's pretty easy to make it to the finish line. Okay, if you don't have enough energy to get up the hill, then there's going to be no reaction. All right, you're going to be stuck over here and you're not going to be able to get to the other side. At the very peak of the hill, that is what we call the transition state. Okay, the transition state. And this is just showing you what's happening. Okay, at that point, that's where the bonds of the reactants are breaking, and then the new bonds are getting ready to form to make the products. Okay, and that is what we call the activated complex. And so on the next slide, I have information about the activated complex. So you can look your notes, and you can see the information on the next slide. The activated complex is a very unstable structure. It's what we call an intermediate or an in-between structure. Okay, it's very unstable. It doesn't last very long. It's like 10 to the negative 13 seconds. All right. And some other things I want you to be able to label on this graph. By looking at the graph, you should be able to determine if the reaction is endothermic or exothermic. Okay. Notice that the products over here are lower in energy than the reactants. Okay, so does this look like it's losing energy or gaining energy? Kind of like when we're talking about endo and exo. Remember, exothermic, it loses energy, and then endothermic absorbs energy. So since the products are lower in energy than the reactants, then this is an example of an exothermic diagram or reaction. Okay, it is losing heat or losing energy, therefore exothermic. You also need to be able to identify or label the delta E, which is also basically the same as delta H, okay, change in energy or the change in heat, okay? So sometimes I'll have it labeled as delta H rather than delta E, so you need to just be familiar with that. So the delta H is the distance here between products and reactants, okay? It's the distance between products and reactants. And then what you also always need to make sure you do, see this dotted line? You always want to extend out the reactant line. So this is where the reactants are starting. You always want to extend out the reactant line, okay? And then the delta H, once again, is the distance between reactants and products. And then the activation energy is distance from reactants to the peak of the hill, okay? So if this is an exothermic diagram, then what is the sign on your delta H value going to be? Remember, so exothermic releases the heat or the energy, therefore your delta H will be negative, okay, have a negative value to indicate that the heat or the energy is being lost. And so this is the information on the activated complex that I was talking about earlier, so I already went over this. All right, you also need to be familiar with the ways to increase the reaction rate. So there are 4 things that you can do. First thing you can do is increase the temperature, okay? Not only do you need to know the 4 different ways of increasing the rate, but you need to know why. Be able to explain why does it make the rate go faster, okay? So remember, when you increase the temperature, you are increasing the kinetic energy. Therefore, you have more collisions, also with greater energy. Okay, remember your particles are moving around a lot more, and so they're moving around faster, being able to have more collisions, get over the activation barrier. Now they can get over the hill a lot faster. Okay, the second thing that you can do is increase the surface area. All right, that's where we're going to break it up into smaller pieces, increasing the surface area. Therefore, there are more collisions. More particles are going to be reacting, therefore more collisions. Then you can get over the hill faster. The third thing you can do is increase the concentration. By increasing the concentration, then you would have more collisions, okay? That means more particles are in solution, they can collide more, therefore get over the hill faster. The fourth thing that you can do is use a catalyst. So we have talked before about how catalysts speed up chemical reactions. So now this is going to explain why or how a catalyst will speed up a reaction. So notice that it says it lowers the EA. So that means it lowers the activation energy. It makes the hill smaller. Okay, so it's a lot easier to run over a small hill than it is a larger one. Okay, so it lowers the activation energy, making the hill smaller, therefore the reaction will go faster. Okay, so not only do you need to know these 4 ways to increase the rate, you need to know the ways to decrease the rate, to make the rate slower. So then it would just be the opposite, right? Therefore, what's the opposite of increased temperature? Decreased temperature, right? So you would decrease temperature, therefore that would decrease collisions. And then you would decrease surface area, you would decrease concentration. And let's see, do you know what is the opposite of a catalyst? Well, the opposite of a catalyst is called an inhibitor. You might have learned this in your biology class. Inhibitor. Okay? Once again, an inhibitor is the opposite of a catalyst. So if the catalyst lowers the activation energy, what do you think the inhibitor is going to do? The inhibitor is going to raise the activation energy. It's going to make the hill even larger, so even more difficult for the reaction to take place. Okay, so here's a diagram showing you the difference between when you have a catalyst. So this one here, the blue curve, is showing you when there is a catalyst, and then the pink curve is showing you the normal reaction with no catalyst at all. Okay, so when we look at these diagrams, you should get in the habit of, so we want to extend out the reactant line. Okay, we're just going to label a few things here. So when you extend out the reactant line, don't forget here the distance between products and reactants. So besides delta E, I usually call this delta H. Okay? Don't forget, reactants are always on the left, products are on the right-hand side. Now notice this time in this diagram, the products are higher in energy than the reactants. So then this is an example of an endothermic diagram. Okay, therefore the delta H value will be positive. So notice that the reactants and the products still start and end at the same place when you add a catalyst. Okay, so notice that the catalyst here that's being added, it just lowers the hill, but it still starts and ends at the same spot. Okay, that's a really important piece of information. Now, what if we wanted to show an inhibitor? So the inhibitor, you would still start at the same spot and still end at the same spot, but you would make the hill even larger if we had added an inhibitor instead. Okay, so you need to know how to label these diagrams and whether the reaction is endothermic or exothermic just by looking at it. Oh, we also need to label the activation energy. So the activation energy is the distance between the reactants to the peak of the hill. So that's our EA, activation energy. Okay, and that is it. That is section 1, reaction rates, for chapter 19. And then the next video will be on section 2, which is equilibrium. Okay, so I will see you later. Bye.